All right, B-Tech students, let's talk about that chemistry exam that's coming up. If you're kind of sick of just drowning in dense textbooks and endless lecture notes, then you are in exactly the right place. Because today, we're going to do something a little different. We're actually going to reverse engineer your exam. I mean, seriously, what if you knew exactly what to study? Not just the topics, but the actual questions that are most likely to show up. Sounds a little too good to be true, doesn't it? Well, just stick with me for a few minutes. Okay, so here's the secret, and it's one of those things that, honestly, most students just completely miss. The B-Tech lore is true. A huge part of your exam. It's pulled right from those back of the chapter questions in your textbook. So today, we're not just studying chemistry. No, we are studying the exam itself. We're going to walk through the exact kinds of questions you're about to face. So, here's the game plan. First, we're decoding the atom's secret address. Yep, quantum numbers. Then we dive into energy, order, and chaos with thermodynamics. After that, it's a ride on the electron superhighway of electrochemistry. Then we'll check out molecules in the mirror with stereochemistry. And finally, we'll lock down your final exam strategy. Sound good? Let's jump into section 1. First up, atomic and molecular structure. Seriously, you've got to think of this as the absolute alphabet of chemistry. I mean, everything we're going to talk about later, from how reactions get their energy to how batteries work, it all starts right here, with understanding the address and the behavior of a single electron. Okay, let's start with an absolute classic. You are going to see this question, I guarantee it, or at least some version of it. It's all over your textbook exercises for a reason. And I know it sounds super complicated, but just think of it like this. Quantum numbers are just the 4 parts of an electron's address inside an atom. That's it. So let's break that address down piece by piece. First, you've got the principal quantum number, N. That's the city, the main energy shell. Then there's the azimuthal, L. That's the street. It tells you the shape of the subshell. The magnetic, M sub L, that's the house number, which way the orbital is pointing in space. And finally, the spin, M sub S, just tells you if the electron inside is spinning up or down. City, street, house, and which way the person inside is facing. See? That's all it is. Okay, this is super important. Let's clear up a really common mistake. The difference between an orbit and an orbital. What you see on the left is the old-school Bohr model, this neat little orbit, kind of like a planet going around the sun. Well, it's not accurate. On the right, that's the real deal, the quantum orbital. It's a 3D cloud, a region of probability. The big takeaway here, we can never know exactly where an electron is. We only know the area where it's most likely hanging out. All right, when you get to the math problems, the numericals on your exam, this is your secret weapon, the de Broglie equation. It's actually brilliant. It connects a particle's wavelength to its momentum. And what does that prove? That tiny things like electrons have this crazy dual nature. They act like a particle and a wave at the same time. This isn't just some abstract theory, you know? It's the reason we have things like electron microscopes. And for sure, you are going to be asked to plug numbers into this to find an electron's wavelength. Okay, so we've got the atom's structure down. Now let's see what happens when they start interacting. Welcome to section 2, thermodynamics. And look, this isn't just about heat. This is about the fundamental rules of the universe, the rules of energy and chaos that decide whether a chemical reaction is even possible. So this really is the million-dollar question in all of thermodynamics, right? Under what conditions is a reaction spontaneous? I mean, why do some things just happen on their own, like rust, while other things need a huge push? Your textbook is obsessed with this question. And the answer? It all comes down to one simple concept. And that concept is Gibbs free energy. We call it delta G. Think of delta G as the ultimate decider, the final boss of a reaction. It's the real, usable energy left over to do work after you account for the total heat change, delta H, and balance it against the universe's tendency towards chaos, or entropy, which is T delta S. This little formula right here, it's basically a crystal ball that lets you predict the future of a reaction. And this is the golden rule. If there's one thing you tattoo on your brain for this exam, it's this. If delta G is negative, the reaction is spontaneous. It just goes, all by itself. If delta G is positive, it's a no-go. It needs help. It really is that simple. Negative delta G means green light, let's go. Okay, moving on, section 3, the electron superhighway, or as your textbook calls it, electrochemistry. This is where chemistry gets really dynamic. We're talking about electrons on the move, zipping around and creating electricity. It's literally a superhighway for electrons, flowing from point A to point B in everything from your phone battery to the rust on a car. All right, now we're hitting the boss level questions. Check this out. The question asks you to calculate delta G and predict spontaneity. See what they did there? They combine what we just learned about Gibbs free energy with electrochemistry. They're giving you electrical data and asking you to predict if a reaction will go. This is a classic exam move. So how on earth do we connect these two worlds? We do it with this, the bridge equation. This beautiful formula, delta G equals negative NFE, is the bridge that connects them. It directly links the spontaneity, delta G, to the electrical potential of the cell, the E naught, which is basically just voltage. The N is just how many electrons are moving, and F is a constant, so don't worry about it. The big idea is that a cell's voltage tells you everything about its spontaneity. And that leads us to golden rule number 2. Look at that minus sign in the equation. Because of that little minus sign, if you have a positive voltage, a positive E naught, you will always have a negative delta G. And what did we just learn a negative delta G means? Yep, spontaneous reaction. It's why your battery works. If it has a positive voltage, the reaction just goes. It's that simple. All right, we've covered electrons and we've covered energy. Now let's get into the actual 3D shapes of molecules with section 4, molecules in the mirror. This is all about stereochemistry, which is just a fancy way of saying that a molecule's physical shape, its 3D arrangement, completely changes how it behaves, especially when you get these weird mirror image molecules. Okay, get ready for this one. I can almost promise you will be asked to tell the difference between an SN1 and an SN2 reaction. It's a massive deal in organic chemistry. At its heart, it's simple. One is a 2-step reaction, the other is a 1-step. Let's break down exactly what that means. So the SN1 mechanism, think of it like a 2-act play. Act 1 is the slow step. A piece of the molecule, called the leaving group, just leaves. It breaks off. This creates a vulnerable, positively charged carbon thing called a carbocation. Then, in Act 2, the fast step, a new group, the nucleophile, swoops in and attacks that carbocation. 2 separate, distinct steps. That's SN1. So here's the absolute dead simple way to keep these straight. SN1, 2 steps. The leaving group leaves first, creating an intermediate. Then, the new group attacks. It's a 2-part story. Now, SN2 is a single step. It's all concerted. The new group attacks from the back at the exact same time the old group is leaving. No waiting, no intermediate. So SN1 is favored by bulky, tertiary molecules that can stabilize that intermediate, while SN2 is for the smaller, primary guys where there's room for that backside attack. Okay, we have covered a ton of ground. We've gone right to the source and tackled the most important, high-yield questions from your textbook. So now it's time for the final debrief. Let's boil all of this down into the absolute must-know laws you need to have in your head when you walk into that exam. These are your unbreakable laws of chemistry for this exam. Law 1, the Pauli exclusion principle. Simply put, no 2 electrons get the same 4-part address. They're all unique. Law 2, Heisenberg's uncertainty principle. You can't know an electron's exact speed and its location at the same time. You gotta pick one. Law 3, the second law of thermodynamics. The universe loves chaos. Entropy is always going up. Law 4, Gibbs free energy. If delta G is negative, the reaction is a go. And finally, the Nernst equation. That's your go-to tool for calculating cell potential when things aren't standard. Nail these down. These are the pillars. So look, we've just walked through the toughest questions from your own textbook. We've decoded the patterns. The questions, the key concepts, the principles, they're not a mystery anymore. You now have the strategy. You have the knowledge. So the only question left is, who's ready to ace this exam? You've got this. Good luck.